homogeneous reactions. Say that we have the recycle reactor. And where we are performing the second order reaction, it gives the product. And here very high recycle. Here void volume of reactor is given as 1 liter. Weight of the catalyst is around 3 gram. Volumetric flow rate 1 liter per hour. Initial concentration of reactant, that is 2 mole per liter. And exit concentration is around 0.5 mole per liter. Okay. Now this is the data which is given for a particular recycle reactor. Now in this particular reactor, we have to calculate the rate constant for this reactor. Rate constant we have to calculate. Now, what kind of the reactor? It is a recycle reactor. And this R is very large. So if R is very large for this particular recycle reactor, it will approximating to mixed flow reactor. So very simple equation. Here, total volume of the reactor will not play, but the weight of the catalyst we have seen in the last lecture. Is it? So it is very simple reaction. 2A gives P, second order epsilon A, it is say that 0, liquid phase reaction. Sorry, it is a non-elementary reaction. So epsilon will be 0 for this particular one. So now the weight of the catalyst is given. Molar flow rate of the reactant will be V0 into Ca0. So it will be 1 into 2 mole per hour. XA out K Ca square. That's it. So it is very easy for this one. So now we can substitute here XA out, that is Ca0 minus Ca out divided by Ca0 into 1 upon A. Ca square is given as 0.5. Is it? So now you can simplify it. Let me know the value of this one. Yes, try to do this calculation. Let me see the value. Yes, anyone? Yes, it is very good too. What is the unit? Because without unit it will be 0. No meaning for this one. What is the unit? Yes, what will be the unit? Try to do it. Find out the unit quickly. Yes, what will be the value? It is 2, but what is the unit? Liter mole hour. Is it correct? Liter square per mole gram hour. It is liter square per gram per mole hour. Gram of catalyst. This is gram of catalyst. This is mole of reactant. Okay. So without unit, this will be the no meaning. Remember. So if you will not write the units, answer will be simply 0, no mass. Now suppose we are performing the same reaction having the rate constant 2 in corresponding unit, that is liter square per gram mole hour. And that is we are performing in a packed bed. Packed bed, that we can say it is a plug flow reactor. We are performing in the packed bed to achieve the conversion 80% having volumetric flow rate of 100 liter per hour, sorry, 1000 liter per hour with initial concentration of 1 mole per liter. So here we have to find out the amount of catalyst. So very straightforward equation from W upon FA0 is equal to what? dxa upon minus ra, is it? So you can easily write it here. It will from 0 to 0.8 dxa a ca0 square. A is known, ca0 square is known, 1 minus xa. You can do the integral, simplify it. Okay, this is v0 into ca0. This is dxa. A is known, that is 2. ca0 is also known, it is 1. So when you perform the integration, you will reach to the value of w. So what is the value of w here? Just try to do the calculation. What will be the w value? Yes, anyone? Very good. It is 2 kg. That's good. So you know the CRE one, that's why you are able to do it the calculations. That's great. In similar case, in this particular part B, if there is a reactor which is packed with one part of catalyst, two, 3 part of inert solids. That means total in that catalyst, suppose there is a one part of catalyst and 3 parts is inert solid. So total amount will be what? And inert. So one part is catalyst and 3 parts will be inert. So total will be 8 kg. So we'll need the 8 kg of that material which is having the one part of catalyst. So depend on the bulk density and voidage, then volume of the reactor will be calculated. Similarly, there is a very simple one more example. That is again, I can say that is a revision of your CRE1. So again PFR with recycle loop 1 meter cube per hour gas. Okay, it is a gas we are passing. Having the concentration 2 mole per meter cube. Total volume of the loop is 0.02 meter cube. 3 kg of the catalyst is needed. Exit stream Ca is 0.5 mole per meter cube. Now we have to find out the rate equation. Rate equation nothing but the, we can say, rate constant for a particular reaction. So there is a case 1. There is a very large recycle. Having the second order and feed as the 50% A plus 50% inert. Okay. Now it is a gas phase reaction. So definitely as per the reaction A gives 3R, there will be the certain value of epsilon. So we have to calculate first epsilon. Yes, anyone can try. What will be the value of epsilon here? Yes, anyone try? Anyone can try. Yes, what is the value of epsilon? One. Is it correct? We can verify it. Okay, whether what will be the value? Yes, it will be the 1. Okay. Because it is 50-50, so 0.5 will get converted, become 1.5 plus inert will be as it is, so 2, and here will be 1. So 2 minus 1 divided by 1 will give you the 1. Now Ca upon Ca0, 1 minus Xa, 1 plus epsilon A x. So from this one you can write the function as a Xa. Now because of very large recycle, it will be similar way W upon Fa0 Xa minus Ra. Is it? So rest of the things you can substitute here, simplify it and get the value of K, and unit will be what? Is again the second order reaction. Take care for the units because it is in meter cube. So units will be We have seen volume square per kg of the catalyst, mole of the reactant per unit time. Is it? But what about this value? Yes, anyone can try. Quickly, go fast. Is it 1.6? You can check it, okay? I don't have the solution. You can just confirm it. Similarly, if you go for the first order reaction, similar way you have to do the calculation and we'll have the certain value and that will be again meter cube for our kg catalyst. Is it? Similarly, you can go for the, because very large recycle, again it will be the third case, no recycle. With reaction, A gives 3R, N is equal to 2, 25% A plus 75% peanut. So in this case, no recycle, it will be simply PFR. But before proceeding, we have to find out the epsilon A. So epsilon A will be 0.25 will become 0.75 and this 0.75, 1.5 minus 1 divided by 1. So it will be 0.5. Is it? So epsilon A will be 0.5. Yes, someone to say 0.8. So for plug flow reactor, W upon Fa0 is equal to Exa and minus Ra is equal to K Cs square or it will be K Ca0 1 minus Xa upon 1 plus epsilon A Xa. Is it? Because it's a change in the volume. Yes. So this value, substitute here, simplify it, do the integration. So it is little bit complicated, but you will get it this value and finally it will be a what? Okay, this you have to substitute and do the integration. The last case, again very large. With N is equal to, So for this particular one, epsilon A will become 0 as per the stoichiometry. And rest is simple, that is because it is a very large recycle. Again, that W upon Fa0 is equal to Xa upon minus Ra. When you simplify it, you may reach to the value K. But make sure that I have calculated this 0.707, but you can verify it. Meter cube mole. Okay. So this will be your answer for the. So this is just the revision of your CRE1 kind. Okay. So check your calculations. These answers may be wrong also, but you use the proper equation, do the integration. If it is a liquid phase reaction, then this epsilon value will be 0 in all the cases. Remember, it was clearly mentioned it is a gaseous reaction. Feed is gaseous, so definitely there will be expansion or the reduction in the volume of reaction mixture. Okay, one more question we can go with. Now the reaction A gives R, that is a gaseous reaction, which is decomposing using a solid catalyst with rate KCA square, second order reaction. Now pilot plant study were performed using the tubular reactor. Tubular reactor that is packed with catalyst with the flow rate having 2 meter cube per hour, that is pure A, and pressure is 200 atmosphere and temperature is 300 degrees centigrade. So this was the condition, and Xa is around 0.65. So this is the case A, and in case B, it is desired to treat around, this is a commercial plant. Similarly, in the tubular reactor, which is packed with catalyst. So now, when we are going for the commercial one, the flow rate of the gas is around 100 meter cube per hour. And the gas is at pressure is around 40 atmosphere instead of 20, and temperature is same, that is 300 degree centigrade. And the gas contains around 60% A plus 40% diluent, we can say that is a simply inert. And here the conversion, expected conversion is around 85%. Now in this case, we have to find out the internal volume of the reactor. Or simply volume of reactor for the case B. In first case, volume is mentioned. Here I have not mentioned. Volume of catalyst is around 2 liter. Okay. With volume is 2 liter. As it is a tubular reactor, it is a plug flow reactor. Is it? So for plug flow reactor, it will be V upon Fa0. V representing the volume of catalyst is equal to 0 to Xa dxa upon minus I. Because here catalyst is given in terms of the volume, not in the weight. So we are writing volume of the catalyst. So it will be as epsilon is 0 here. Elementary reaction 1, sorry, non-elementary with the 1 stoichiometric constant. So it will be, epsilon will be 0. If you do the integration, it will become 1 upon K Ca0 square Xa upon so for pilot plant, we can write it V1 Fa01 is equal to 1 upon K Ca01 square Xa1. We have to perform the same reaction so that this K will be as it is. It will not change. We have to find out the reactor volume in terms of the volume of catalyst. Commercial plant, this will be V2 Now for these two cases, we have to find out the initial concentration because Fa0 is equal to V0 into Ca0. So Ca0 1 will be Pa01 RT. So this will become 20 into 0.08206 into 570. So it will be around 0.4253 mole per liter. Okay. So Ca0 you can calculate. Similarly, you can calculate the Ca2, Ca02. Here, remember, it will be partial pressure of A RT2. So here total pressure is around how much it is 40 atmosphere and gas is A is 60%. So 40 into 0.6 will be the partial pressure. R will be 0.8206 in corresponding unit. temperature is same, so it is 573. So this value will become, it will come around 0.5. So it is 0.104 mole per. So this way you will have the value of Ca0. Then rest is the very simple. You can just divide 1 by 2. So it will be V2 upon Fa01. Sorry, Fa01 divided by V2. And this will be equal to KCA0 1 square KC square. So Kk will get cancelled, all other values are known. So you can calculate the V is the 254 liter of catalyst. Okay. So very simple, that simply based on your CRE 1.
स्टार्ट होने की क्लास.
Okay, we'll go for some more examples. This one more example we can see.
Sir, value of epsilon is not 0, I think, in second case. Hello, sir.
Yes.
Hello. Sir, the value of sir epsilon, sir, I think is not 0 in second case. Sir, how you can write that equation V2 by F not 2 equal to KCA not squared, and sir, directly XA2 by 1 minus XA2.
In second case,
Sir, the value of epsilon is not 0, no, sir. Sir, 60% A and 40% sir inert.
it is 60% A and 40%. It is
Inert.
a diluent. Diluent is liquid. It is not the gas. Diluent will not expand. Remember, it is a liquid one. Gas
Okay,
is
sir.
60%. Okay. Gas is there.
Okay, sir.
Diluent represent doesn't mean that there is a gas. It is a liquid kind of thing. Only this will total pressure will be contributed in this one. Okay. So that's why we have not taken that epsilon will be the with this respect to. Here it is a diluent. Generally, diluent we use it to mediate the reaction in case of the gas phase reactions.
Okay, sir.
Okay. Now you have already performed the done various calculations to find out the rate expression based on the various data, say that the changing the volumetric flow rate and getting the conversion, or changing the concentration and getting the conversion, and based on that you are able to find out the rate expression. Okay, so finding out the rate of particular reaction. So similarly we are performing the experiment in, say, that particular reactor, experimental reactor. And that is a gaseous one. A gives R. So pure gases we say. So it will be the epsilon will be 0. And reactor is mixed flow. And for various volumetric flow rate, so that here I'll write it. That is 3 to 1.5. XA is observe, and that is 0.2, 0.3, and 0.5. And for this particular case, fix the weight of the catalyst, that is 4 gram, and initial concentration as 10 mole per meter cube. Now we have to find out the rate expression. Okay, and that will be what? Ra is equal to K Ca, is it, to the power n. So from this given data, what we can calculate? To find out this particular rate expression, we have to know the value of Ra first, because by taking ln minus Ra, then you can get the, sorry, ln Ca, is it? So by plotting this one, you can get the n value and the K value, order of the reaction. So Ra we can calculate from this one. Ca we can get it. Ca0 is given, Xa is given. So Ra we can easily calculate. X Ca upon Ca0, 1 minus Xa. So Ca we can get it for various value of this protein. So 0.8 into 10, that will be 8. So it will become 8, 7, and 5. What about the Ra? It is a mixed flow reactor. So it will be Ca0 V Xa upon weight of the, is it, because this is Fa0 W Xa. So when you are going to calculate it, what will be the values? 15. It will come the same value, say around 15, 15, 15. So what you can say about this one? If rate is constant, what will be the order of reaction? If rate is constant, then order of the reaction will be what? Anyone? Zero order. Very good. So order of the reaction will be zero order. So Ra is equal to K, and that is equal to 50. And units will be as per this moles per hour per gram of the catalyst. So this is all examples. Almost I think these are the base on the your CRE1. Only difference is here we are calculating the weight of the catalyst instead of volume of the reactor. So now we'll, in the next lecture we'll go for the few more examples which are just related with the intraparticle diffusion is there or not. So based on that we'll find out the certain whether effectiveness factor will be 0 or sorry, it will be 1 or less than that. So examples, solved example, unsolved examples, almost up to 90. I think all are based on your CRE1 itself. Very simple examples. So whatever you feel it, few examples you can do it from this chapter. And if you have any difficulties, you can ask me later. Okay, you can put it, what about this particular exam? Okay, few more examples we will see in the next two lectures, Friday and Saturday, because there are number of unsolved examples having the different varieties, means the difficulty level. Okay, so if you have anything, you can ask me now, or you can put it later on also on WhatsApp. Or maybe after completion of this chapter, we'll have some difficulty session. If you have any difficulties, we will solve that. Okay. So if you have no questions, you may leave, no problem.